Hi everyone, we're Group 2 and welcome to our final presentation. Let's just dive straight in. So here's the motivation.
Stay in the moment with complete control over what comes next, at least when it comes.
As you can see in the video, many existing music platforms interrupt the listening experience with frequent advertisement. For example, in just 30 minutes of listening, users can waste up to 10 minutes on ads alone, which completely ruins the music experience. Besides that, music listeners and curators often struggle with disorganized and decentralized music collections, making it really difficult to find specific tracks or arrange songs for continuous listening. To fix this, we developed our music library management system as a complete platform where users can seamlessly discover and manage music, while administrators can efficiently control the global library. And the best part is completely free. Our application includes secure authentication, music playback controls, smart recommendations, advanced search, playlist and favorites management, and account management as well. For admins, the system also supports library management features such as handling songs, albums, and today hits content. Compared to our original proposal, we further improved the UI design and added curated discovery sections and favorites personalization to
This is our demo session. As you can see on the screen, there is a um, interface of our app and also the console log and the file-based real-time database for you to track the activity more easily. Okay, now you click into the sign up button and create a new account. When clicking to the sign up button here, you can see that there is a message that see that it has created the account successfully and also has the information stored in the database here. Okay, if we move into the main view here, and you can see that there is a feature in the songs. I click into one song here. Another sunrise. And we move to another song. And I will play the previous song and also the next song. Okay, you can see there is also the activity track in the console log. Okay, now I will play a hot button here. You can see that it also change the has a signal of a change in the playlist note here, which means that there is a change in the favorite song playlist. You can see that it also changed in the UI here in real time. And now I will create a new playlist here, named Study Music. And when I click into the done button, you can see that there is a signal change in both the playlist and users. It create a new node in the playlist, also pivot the playlist IDs section of this user into a new limit playlist. And now I will type a song here. I will type by the artist name and I will add it to the playlist. Okay, when I click into the artist playlist here, you can see that there is also a change in this playlist. It pivot into another song ID here, and also change in the UI. Okay, and you will log into the admin view. I will add a new album here, and I will type the information. As you can see, I have the image thing here, Y, and I will upload the Google Drive link here. And when I click into the Save to Database button, you can see that there is also a change in the album, which creates a new note for this album. Okay, now we add this song to this album. I also store the audio by the Google Drive link. Step here, and you will see that there is also a change in this file base, and it's pivot into a new song, and that's all.
Now, let's dive into the core data structure of our system. First, we use a stack to manage the user's navigation history. Every time a user opens a new view, we push it to the stack. This guarantees an instant O1 back button experience. For music playback, we manage the queue using a linked list. This allows seamless insertion and removal, making next or previous track navigation instant. Next, to display the latest song or newest album release, we implemented a priority queue based on a min heap. Instead of sorting the entire database, it automatically ejects older songs, keeping only the top newest tracks. This optimizes our filtering down to O and locate time. To make the application fast and save network bandwidth, We built an in-memory hash map as a local cache. It provides a one constant time lookups, which drastically reduces our API calls to Firebase when the UI refreshes. And finally, the backbone of our search engine is a self-balancing AVR tree, acting as an inverted index to store keywords. For multi-word queries, we pull the initial song pool from the primary pivot node and load it into a temporary hash set. This allows us to dynamically filtering the pool down to exact intersection of matches efficiently.
On to our algorithms. First is our deterministic user ID generation. Instead of random strings, we use a polynomial rolling hash to translate user emails into integers. To resolve ID collisions safely on the client side, we combine the multiplication method with double hashing. We even use bitwise operation to force an odd step size. This strictly prevents infinite loops and allows our hash table to dynamically double its size without breaking. And second is our prefix search traversal. When the user types a multi-word query, we tokenize the input. We traverse the AVL tree to quickly fetch candidate song for the longest word. Then we use a hash set remove if function to filter out songs that don't match the remaining words. This approach gives us a highly efficient O-log and plus R search time, significantly outperforming standard array iteration.
Moving to system testing, to validate our complex algorithm, we execute a dual-layer strategy aimed at 100% reliability. We perform terrified automated unit tests on call structure, followed by comprehensive end-to-end manual testing, and consequently, we achieve a percent 100 pass rate across all test cases. To conclude, I would like to highlight four limitations. The first is security. We plan to integrate bcrypt encryption to ensure secure credential hashing, the real-time synchronization. So we'll move to Firebase Value Event Listener to ensure all clients stay synchronized instantly. The performance. We aim to serialize the AVL tree structure locally to reduce startup time. That also concludes our presentation. Thank you for listening.